Hi everyone, this is your first recording online. I hope you're all doing well. I am going to do a few recordings for you and see how they go. The topics I'm going to do are the chapter on probabilities, or all of probability. I'm then going to go on to statistics, and then I'm going to do the proofs by induction. And then we might regroup and see how we are after all of that. The books that I'm using are the Concise Project Maths books. You'd have seen me using these here in the house. So I'm going to use that, and then I'm also going to hop to an iPad where I'm going to work some of them out. It doesn't matter that you don't have this book. You can pause the video at any time. Try and do some of the examples. I have the answers here, so I can check any of them for you at any stage. So send me a message, and then at some stage when it makes sense, I'm going to try and do a live class with you, which will be like more a tutorial where you log into a live classroom and you ask me questions on some questions that I have set you. So that's the plan for the next couple of weeks. Let's see how it goes. So this recording I'm going to do permutations and combinations, so some of the probability chapter. So let's start with the theory. So when you do an event, or when you do an operation, the output of that, or the result of that, is what we call an outcome. So in other words, if you throw a dice, one possible outcome is the number 5. Another possible outcome is the number 6. If you flip a coin, a two-sided coin, then possible outcomes, there's only 2 possible outcomes there, heads or tails. So that leads me on to the fundamental principle of counting, which you must actually know the definition of. I have seen exam papers ask, what is the fundamental principle of counting? And the answer to that is the following definition. Suppose one operation has m possible outcomes and a second operation has n outcomes, then the total number of possible outcomes is m multiplied by n. Slightly different definition to that is, suppose one event has m possible outcomes and another event has n possible outcomes, then the total number of outcomes is the product of the two, m by n. When you perform one operation and another one, that brings me to the AND law of probability, which I will come to in the next recording. But it means you multiply your answers together. So in other words, because that first operation, or that first event, had m possible outcomes and the second operation had n possible outcomes, if you're listening closely, you will have heard the word and in the middle. Anytime you hear that word and, it means multiply your outcomes together. So m by n. Okay, typical question that gets asked on this could be menu options. If I had 3 choices for starter, I had 4 choices for main, 3 choices for dessert. How many menus or dinner options could I come up with in total? So that's 3 multiplied by 4 multiplied by 3 again, so that's 36 different outcomes. Okay, so the example there, if a regular 6-sided die is thrown and a coin is tossed, how many different outcomes are there? Part 2, write out all the possible outcomes. Okay, when we're doing anything related to permutations or probabilities, if you have 2 events, as is such here, you throw a dice and you toss a coin, then you have 2 different boxes for the values they contain. So there's 6 possible outcomes for the dice, so that's 6. There is 2 possible outcomes for the coin, that is 2, and therefore the total number of outcomes when you throw a 6-sided dice and you toss a coin is 6 by 2, which is 12. Okay, to write out all the possible outcomes, you can do this in a number of ways. You can just logically go down through heads or tails and the number, heads or tails again and the number. So in other words, I have 1 with heads, I have 1 with tails. I have 2 with heads, I have 2 with tails. Or you can do it out in such a table like this, or you could even do a tree diagram if you so wish. It doesn't matter which option you take, as long as somehow you have a system for writing out all 12 different outcomes. So that's the fundamental principle of counting. Alright, permutations then. What is that? A permutation is an arrangement of a number of objects in a definite order. So the questions that often come up on this are arranging books on a shelf, or arranging people in a line, so on and so forth. So it's an arrangement of a number of objects in a definite order. On our calculator, we use NPR for permutation. If you look at your Casio calculator, it's the multiplied sign, it's sitting behind it. So consider the 3 letters P, Q and R. If these letters are written down in a row, there are 6 different possible arrangements. P, Q, R is 1. P, R, Q is the second one. Q, P, R is the next one. Q, R, P is the fourth one. Or P, Q is the next one. Or Q, P is the last one. Okay. So yes, you can write out all of the different outcomes. That's called the sample space when you write out all of the different outcomes. Or you can do it as in how many options did I have for my first letter? Well, I had 3. I had either P or Q or R. Okay, then we put one of those letters in place. How many options did I have for the choice of second letter? Well, I was down to 2 because one of the letters is fixed here in position 1. So then I have 2 options for the second letter. Now I have those 2 letters in place, so I'm down to just 1 option for the third letter. So 3 by 2 by 1 is 6 ways that those 3 letters can be arranged. Okay, again, the boxes are an aid in helping to fill out the number of ways each choice can be made. And I'll come back to the boxes again and again and again as I go down through this. Okay, of course there's a formula. If we have n different objects to arrange, then the total number of arrangements is what's called n factorial. Factorial is just maths language, maths shorthand for writing that number all the way down to 1. So in other words, 5 factorial is 5 by 4 by 3 by 2 by 1. 10 factorial is 10 by 9 by 8 by 7 by 6 by 5 by 4 by 3 by 2 by 1. In general maths notation, n factorial is n, which is the number we start with. Take 1 away from it, n minus 1. Next number, go down 2, n minus 2. Third number, go down 3, n minus 3, and so on and so forth, until you get towards the end by 3 by 2 by 1. Okay, that's factorial. Factorial button does depend on which calculator you have. On the old Casio calculators, I think it sits behind the ABS button. On the new calculator, the Casio calculator that came out this year, I believe it sits 3 rows down, 3 across, so behind the X minus 1 button. Okay. So at the end then, we have an example. Suppose we have 5 different objects and we want to find the number of possible arrangements taking 3 objects at a time. We could use the fundamental principle of counting 1 for this. Okay, so I am arranging 3 objects at a time. So again, I have 5 different objects, so I have 5 options for that first object. One of them is now in place. I'm down to 4 objects for my second one. Those 2 are in place, and I'm down to 3 objects for the third one. So when you go 5, and because it's and, one object and 2 objects and 3 objects, you end up multiplying all the values together. So you have 60 different ways, 60 different possible arrangements where you can take 3 objects at a time from a pile of 5 objects. Okay, there is again a formula for this. We can do it using factorials. Okay, I'm going to go on to the next page, which gives you the official formula for it. It is the total number of arrangements, so that would be 5 factorial in this case, over 5 minus the 3 that I need to arrange factorial. Okay, now let me go back and show you that in operation. So in this case, my 5 objects was 5 by 4 by 3 by 2 by 1, so that's my n factorial, or 5 factorial in this case, divided by 5 minus 3 factorial, which is 2 factorial, which is 2 by 1. So what ends up happening is the 2 cancels with the 2 at the bottom cancels with the 2 on the top, the 1 on the bottom cancels with the 1 on the top, so you are left with just 5 by 4 by 3, which is what you had from the fundamental principle of counting. So you can do this in either way, it doesn't matter at all. Okay, the quicker way of doing this formula is programmed into your calculator using that NPR button that I spoke about, the one that sits behind the multiplied sign, where n is the total number of objects you have, or is how many you're choosing. So on your calculator, if you go 5 NPR 3, you should also get 60 that we got when we did it with the fundamental principle of counting. Okay, fundamental principle of counting 2. Suppose one operation has m possible outcomes and that a second operation has n outcomes. Then the number of possible outcomes of the first operation or the second operation is given by m plus n. What's the difference? It's the wording. So in fundamental principle of counting 1, which is the normal one taken for the fundamental principle of counting, and it's the only one that's on the ordinary level course, the number of possible outcomes when performing the first operation followed by the second operation, and I could use the word and in there instead of followed by as well, is multiplied. In this one, the wording is the number of possible outcomes of the first operation or the second operation is m plus n. The way I remember it is that when it's or, you're not as fussy, so you will take either of these, so you end up with adding them together. And again, I will come back to this and or again when I'm doing probability, because there's a similar formula in, or similar law of probability called the and or laws of probability, where I'll come back to this, and it will mean multiply and plus as well. So how do these questions get worded? Well, look at example 1. A bag contains 9 discs numbered 1 to 9. A disc is drawn from the bag. If the number is even, then a coin is tossed. If the number is odd, then a 6-sided die is thrown. How many outcomes are possible? So the only way you can do this is to logically break it into little steps. Don't think of these as one big entire problem. The only way you will get to it is to literally, like you put blinkers on and you take it piece by piece. So let's have a look at the first experiment, okay? If the number is even, well, how many numbers are between 1 and 9? Even numbers. Well, there's 4. Then a coin is tossed. So in the first experiment, we get an even number and the toss of a coin. So we get 4 multiplied by 2. So there's 8 different outcomes for that first experiment. We can get the number 2 heads, 2 tails, 4 heads, 4 tails, 6 heads, 6 tails, 8 heads, 8 tails. So that is 8 possible outcomes. Okay, the second experiment, because it could also be an odd number, well, I have 5 different odd numbers, and then a 6-sided die is thrown. So 6 options there. Now I'm not going to call all of these out because 5 6s are 30, but I will start it off. So it could be the number 1 from the disc with 1 from the die. It could be 1 from the disc, 2 from the die, 1 from the disc, 3 from the die, and so on and so forth. So I can get an even number or I can get an odd number. So that is why we add those outcomes together. So there are 38 possible outcomes from that event. Example 2. How many arrangements can be made of the letters P, Q, R, S and T, taking 2 letters at a time if no letter can be repeated? Okay, and there's a few ways of doing this, and it depends how your brain thinks. The first way will be much easier to sum, in that for that first letter I have 5 different options, P, Q, R, S and T. Okay, I can't repeat any of the letters, so one of the letters is fixed there. So for my second letter I'm down to 4 options for the second letter. So there's 20 different arrangements that can be made taking 2 letters at a time from P, Q, R, S and T. Okay, you can use it with the formula here, which is 5 factorial over 5 minus 2 factorial, 5 being the total number of letters that I had, 2 being how many I was taking at a time. So it's 5 factorial over 3 factorial, which again gives you 20. Or the third method, on your calculator you're doing 5 P2 and you should again get 20. Okay, so example 3 then. How many different arrangements can be made from V, W, X, Y and Z? So again 1, 2, 3, 4, 5 letters, taking all the letters at a time if V must be second and Z can never be last. Okay, so I might do this one for you. I have my book in front of me just in case anybody's wondering how I can remember the sum. So let me share this with you now. Okay, so how many different arrangements can be made from the letters V, W, X, Y, Z, and my conditions: V must be second, Z can never be last. Okay, so how I do this one is I will create 5 placeholders because I'm arranging all 5 letters. Okay, so it'll be letter 1 and letter 2 and letter 3 and letter 4 and letter 5, so they're all multiplied. So you do your conditions first. V must be second. So how many options have I for that second letter? Well, I only have one option, that's the letter V. Okay, let's go to my second condition. Z can never be last. So I have V in place. Z can never be last. So can you see that I have just 3 options for my last letter? Z can't be last. Okay, I hope that makes sense. That's what happens when they put restrictions on it. So then I start looking at what then do I have for my first letter. Well, I have 2 letters in place. I have 3 left here. I have 2 left here. And I have 1 left here. So maybe to explain that a bit more. Okay, so why have I only 3 here? Because Z can be here. Well, I have a letter placed here, a letter placed here, so I'm down to just 3 letters for that location. Now I have 3 letters in place, so I've only 2 for there, and I've only 1 for there. And when you put that into a calculator, 3 3s are 9, 9 2s are 18, out comes. Okay, how many different arrangements could have been made if there was no restrictions? Well, that's 5 factorial. If you think about it, I have 5 options for the first one, 4 for the second one, 3 for the third one, 2, 1, and 5 factorial is 120, I think. Yeah, 120 outcomes. Okay, so that's how we work permutations when we have restrictions. In some questions we make use of the following fact. The number of arrangements when an outcome does not occur is the total number of arrangements minus the number of arrangements in which the outcome does occur. Okay, and this example 4 here would be quite a common one in a Leave and Cert exam paper. A, B, C, D, E and F are 6 students. In how many ways can they be seated in a row if there are no restrictions on the seating? That's easy enough, that's 6 factorial. A and B must sit beside each other. Okay, so I recommend you pause the video here now, take down the question, and then I'm going to go and work it out for you. Okay, so A, B, C, D, E and F are my 6 students. So no restrictions. You can do that for 6 factorial if you want, or 6 by 5 by 4 by 3 by 2 by 1, because that is what 6 factorial is, and that works out to be 720 ways in which 6 students can be seated in a row. So swapping them around in all of their different permutations results in 720 different ways they could be seated. Okay, the second part said A and B must sit together. Okay, so how we do that is we treat A and B as one permutation. In other words, we move them around together. So we've AB, we've C, we've D, we've E, and we've F. Okay, so now can you see I just have more or less 5 different arrangements. So I don't have 6 anymore because A and B are effectively stuck together. Okay, so these 5 can be moved around in 5, so 1, 2, 3, 4, 5, by 4, by 3, by 2, by 1 ways. In other words, that's I'm counting as 1, so 1, 2, 3, 4, 5 options here. I've put 1 in place, and that could be A, B together. It doesn't matter where A, B goes, they go right after each other, by 4, by 3, by 2, by 1. Okay, so that's the first bit of it, but what you have to do then is you have to multiply it by 2 factorial. Okay, why? Because it says A and B must sit together, but I have AB or I have BA. Okay, and either of those combinations gives you A and B still together, but it does increase the number of permutations you can have with the 6 letters and still have A and B sitting together. Okay, so where did I get 2 factorial? Well, I have 2 objects that I need to arrange. So for the first one, I can have A or B at the start. I put one of them in place by 1. So you can write it down as 2 or 2 factorial. Either way, the answer is 2. So that's me arranging the 5 above. And this one here is AB or BA. So even though A and B have to be together, AB is as good as BA. So 5 factorial then gives me 120. 2 factorial gives me 2. So there's 240 ways that you can arrange A, B, C, D, E and F while having A and B sitting together. Okay, the third part asks for A and B must not sit together. Okay, now that's quite difficult to work out directly, so we get it indirectly. Okay, so they must not sit together. And that's still A and B that I'm talking about. Okay, so this is total permutations. It's the easiest way to do it. Minus A and B together. So look out for this question in your Leaving Cert. If you get a permutation question, it comes up quite a bit. So I take the ways in which they are together from the total permutations, and it is the easiest way then to get the number of permutations, the number of ways in which A and B cannot sit together. Okay, so that was part 3. Part 4, D, E and F must sit together. So this is the same as above. We create a box for D, E and F, and then I also have A, B and C. So can you see I really only have 4 arrangements there. However, D, E and F can be arranged in 6 different ways. 3 factorial, so 3 options for the first letter, D, E or F, 2 options for the second letter, and 1 option. So that's a 3 factorial, is just the shorthand way of writing it. So 3 factorial by 4 factorial is 3 2s are 6, 4 3s are 12, 2 2s are 24, so 144 different ways. And then the last part of this question, A and F must sit at the end of each row. So I have 6 letters, A, B, C, D, E and F. A and F must sit at the end of each row. Okay, now it's not telling me A has to be at the start and F has to be at the end. Okay, so that's interchangeable, so I'll have to multiply my answer by 2. I'm going to set it up for, well, there's a couple of ways I can do this. I could set it up for having 1 option which is just A at the start and F at the end. So that's those 2 in place, by 4, by 3, by 2, by 1. Okay, and then I multiply it by 2, which is then going F at the start and A at the end. Okay, or, so that gives me 48 options, or I could have gone, I have 2 options for my first letter, A or F, which means then I have only 1 option for my last letter, whichever one I didn't use at the start, 4 options for my third, 3 options for my fourth, by 2, by 1, and you would also get 48. So whichever of those 2 bottom makes more sense. Okay, and that's that example. Okay, example 5 comes up quite a bit as well. How many different 4-digit numbers greater than 6,000 can be formed using the digits 1, 2, 4, 5, 6 and 7 if number 1, no digit can be repeated, 2, repetitions are allowed. So 4-digit numbers, okay? So that's why there are 4 boxes, because it's a 4-digit number. So they have to be greater than 6,000. So you see that first digit here, this is with no digit repeated. That first digit there, I only have 2 choices for it, 6 or 7. Okay, so that's why that's 2. So I put one of the digits there, and then 1, 2, 3, 4, 5, 6. I have 5 options for my next digit, 4 options for the next digit, 3 options for the next digit. So 120 numbers can be made from 1, 2, 4, 5, 6 and 7 if no digit can be repeated, and they have to be greater than 6,000. If repetitions are allowed, well, I still only have 2 options for that first number, because it still has to be greater than 6,000, so it can be 6 or 7. However, I can have any of the 6 for my second, third and fourth digit. Okay, so permutations. So example 6, how many different 5-digit numbers can be formed if from the digits 1, 2, 3, 4 and 5 if there are no restrictions on digits and repetitions are allowed? The number is odd and no repetitions are allowed. The number is even and repetitions are allowed. The number is greater than 50,000 and no repetitions are allowed. Okay, so again, pause, take that one down, and I'm going to do it here for you. Okay, so we have the numbers 1, 2, 3, 4 and 5. No restrictions. Okay, no restrictions, repetitions allowed. Okay, why is that important? Well, it means this is not a 5 factorial. So 5-digit numbers. So 1, 2, 3, 4, 5. How many options have I for that first digit? Well, I have all 5. I am allowed repetitions. So I still have 5 options for the second one, 5 for the third, 5 for the fourth, 5 for the fifth. Okay, remember what 5 factorial would be? 5 by 4 by 3 by 2 by 1. So factorial automatically assumes that no repetitions are allowed. Okay, so it's not that in this case. Okay, 5 by 5 by 5 by 5 by 5 is 3,125. 5-digit numbers can be formed from 1, 2, 3, 4, 5 with repetitions allowed. Okay, part 2. The number is odd and no repetitions are allowed. So again, still 5-digit numbers, 1, 2, 3, 4, 5. Okay, so what makes a number odd is this number out here. So I have odd, 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 even and even. So I have 3 different options for that odd number at the start. So this one is odd, no repetitions. So no repetitions, which means I have one of the numbers already used in that location there at the end. So that means then that I have only 4 options left for my first number, 3 by 2 by 1. So 72 different numbers that are odd with no repetitions. Okay. Part 3. So the number is even with repetition. So again, 5-digit number, 1, 2, 3, 4 and 5. even, I only have 2 options for the end, but I can use all 5 numbers there, all 5 numbers there, all 5 numbers there, and all 5 numbers there, because I'm allowed repetition. So 1250. Okay, part 4 then. The number is greater than 50,000. No repetitions. So again, 5-digit number. Greater than 50,000, so it means this one has to be a 5. So I've only one option there. No repetitions, so that can be any of the remaining 4 numbers, any of the remaining 3 numbers, 2 numbers, and 1. So I actually have only 24 permutations of that. Okay, so permutations, how to arrange stuff. Okay, let's have a look at some of these examples and see what could be done. Question 4 is worth doing. So can I suggest that you tackle question 4? So if you on WhatsApp go question 4, page 257, and share the answers when you have it done. And perhaps question 5. So 4 and 5, they're worth doing. Work together, work separate, I don't mind. But do run your answers by me and see are they right. Okay, and of course there's any number of them. Let me go a little bit slower. If you so wish, you can pause on this page and you can do more, and I will check them for you, no problem at all. So if this is a topic that just your brain isn't tweaking with permutations, because it is a way of thinking, then please do more of them. I will check any number of them, no problem at all. I will do a tutorial on it where I show you how to work some of them, no problem at all. You decide how much practice you need at this. Okay, so that's permutations. And it would be lovely if it was just permutations, but there is also a selection process called combinations. Okay, now how is a permutation different to a combination? Well, a permutation, if we pick, I'm just going to share my notepad with you. Okay, so a permutation is arranging 5 people let's call them Anne, Barry, Chloe, Daniel, and Eve in a row. Okay, how many ways could these be arranged? Okay, well, if I come up with the permutation of Anne followed by Barry, followed by Chloe, followed by Daniel, followed by Eve, that is a different permutation to A, C, B, D, E, which is a different combination to that one, which is a different combination to this one, and so on and so forth. So in fact I have 5 factorial, so 100 different ways of arranging those 5 people. Okay, that's a permutation. Keyword being arranging. That is an absolute keyword. They won't tell you it's a permutation, but they will have the word arranging there. Okay, combination then. Okay, choose a team of 3 people from Anne, Barry, Chloe, Daniel, Eve. Okay, so if I choose a team which is Anne, Barry, Chloe, Okay, can you see that is the same team as Barry and Chloe, which is the same team as Barry, Chloe, Anne, which is the same team as Anne, Chloe, Barry, which is the same team as Chloe, Anne, Barry, which is the same team as Chloe, Barry, Anne. So all of those 6 would have been 6 different permutations, but I am telling you it is just one combination of a team of 3 people from those 5. So combinations are quite different, and there's a lot less combinations than there is permutations. They are the same team of people, so that just counts as one combination. But if it had been a permutation, there would have been a lot more. It would have been 6 different ones. Okay, so permutations, combinations. So you're looking for choosing. The word choosing is a real keyword when it comes to combinations. Okay, so combination is a selection of a number of objects in any order. In making a selection of a number of objects from a given set, only the contents of the group selected are important, not the order in which the items are selected. For example, AB and BA represent the same selection, but AB and BA would have been different arrangements. Okay, when we're talking about combinations, we use this notation N choose OR, that's what that is called. So it is the NCR button on your calculator, which on a Casio is above the divide by sign. Of course, it has its own formula. It is, again, you'll see the n factorial on the top. You'll have the n minus or factorial on the bottom, which would have been the same as permutations, but also on the bottom is now or factorial. Okay, needless to say, I don't ever remember the formulas. You know how well how good I am at formulas, so I will do all of this using the NCR button. Okay. For example, let's go to example 1. 10 people take part in a chess competition. How many games will be played if every person must play each of the others? Okay, how many people play in chess? 2. So you have 10 people to choose from, of whom we want to choose 2 at a time. So out of the 10, I'm choosing 2. So I have 45 different combinations of 2 people from a group of 10. Okay, so onto your calculator you do then shift the divide by sign, so NCR2, and you will get your 45. Okay, example 2. In how many ways can a committee of 4 people be chosen? And you can see that word chosen coming up. That's a combination. That's an NCR. On your calculator, that's a 10 choose 4, which will give you 210. Okay, so that is the number of ways 4 people can be chosen from a panel of 10. If a certain person must be on the committee, in how many ways can the committee be chosen? Okay, I'll show you how I would do that one. Okay, so I have, just flick onto the page in the book. So I have 10 people to choose from. Okay, and the committee is 4 people. Okay, so in how many ways? Well, the first one was 10 choose 4, so on your calculator it's 10 C4, which is 210 ways. Just check that. It's 210 ways that you can choose a committee of 4 people from a group of 10. Okay, part 2. A certain person must be on the committee. Well, then I have that one person, and then out of the 9 remaining people, I'd like to choose 3. Okay. And then the third part, if a certain person must not be on the committee, remember that word not is key. I will go total minus the certain person on the committee. So it's 210 minus the 84 equal to 126 different ways of choosing a committee without that one person. Okay, in how many ways can a group of 5 be selected from 9? That's 9 choose 5. How many groups can be selected if 2 particular people from the 9 cannot be in the same group? Okay, so in order to calculate how many groups of 5 can be selected if 2 particular people cannot be included, we first need to calculate the number of ways of selecting 5 people with these particular 2 people always included, i.e. we have 7 from which we choose 3. Okay, there's a typo here in the book. That should say 5 choose 3 or 7 choose 3, not 7 choose 5. So that's a typo there. That should be a 3. Okay, so now we've picked the 3. So the number of ways of selecting a group of 5 people from 9 when 2 particular people are not to be in the same group is the total number of ways of selecting 5 from 9, which is the 126 we got at the top, minus the number of ways of selecting 5 people from 9 with those 2 particular people in it. Okay, so 91. Okay, and then there's another example there that you can go through. I want you to try some of these, the NCRs. The NCRs are going to come up again and again and again. The NCRs is by far much more widely used than permutations. We will use it in Bernoulli's trials quite a bit. Yeah, we're going to use it quite a bit throughout your statistics course. Okay, so let's have a look at some of these examples. I'm going to assume that you can put NCRs into the calculators, so I'm going to ignore the top ones. Question 14 looks okay. Let's try that. And let's try question 17. And again, page 265, post me those answers in WhatsApp. Okay, so what happens when you have to take combinations from 2 different groups? So I'm here now on page 267. Sometimes we have to deal with problems choosing objects from 2 different groups. This involves choosing a number of objects from one group and then choosing a number of objects from the other group. There's 2 key words when we apply the fundamental principle of counting. If you see the word and, you're going to multiply. If you see the word or, you're going to add. So for example, how many different basketball teams, each consisting of 3 boys and 2 girls, can be formed from 7 boys and 5 girls? So again, take that one down and let's pause. Okay, so we have a team has 3 boys and 2 girls. And in my class to pick from, I have 7 boys and 5 girls. So how many different basketball teams can I get? Well, out of the 7 boys, I'd like to choose 3 of them for my team. So n choose over that, and you get 35. Then out of my 5 girls, I'd like to choose 2 of them, and I get 10 options for that. So I need the 3 boys and the 3 girls, which is why you end up multiplying them to give you 350. Okay. So it's these keywords all the time that you're going to be looking out for. There are 5 women and 4 men in a club. A team of 4 has to be chosen. How many different teams can be chosen? If there must be exactly 1 or exactly 2 on a team. Okay, we have 5 women and 4 men, that's what it told us in the club, are always the upper numbers in the combination. A team must consist of 4 people. Okay, so let's try this one. How would we do this one? Okay, so exactly 1 or exactly 2 women on a team. Okay, and I have in total 5 women and 4 men in the club. Oh, I have mean instead of men. Okay, so exactly 1. So out of those 5 women, I want to choose, so that's 1 woman, and if there's going to be 4 on a team, then I'm going to need 3 men to be the other people on that team. So out of the 5 women, I want to choose 1 of them to be a woman, and out of the 4 men, I want to choose 3 of them for my team. Okay. If you put that into calculator, you'll get 20. So all of those are choosing. Exactly 2 women. Well, 2 women and 2 men. Okay, because there has to be 4 on the team. So out of the 5 women, I'm going to choose 2 of them. And out of the 4 men, I'm going to choose 2 of them. And I get 60 for this. Okay, now see this keyword up here? I am happy with my team if it's exactly 1 or 2 women. So 1 woman was 20 from here, 2 women was 60 from here, and that word or means I add them. So I have 80 different teams that would consist of 1 woman or 2 women. That one's now harder. Oh, and there's the solution. Okay, how many bundles of 5 different books can be made from 8 maths books and 6 physics books if the number of maths books must always be greater than the number of physics books? Okay, so again, logically think about what you're asked. So if you have 8 maths books and 6 physics books, and there are always the upper numbers, they're always the upper numbers. So a bundle must consist of 5 books, and you need to have more maths books than physics books. So therefore, what are your options? Well, you can have 5 maths books and no physics books, or 4 maths books and 1 physics book, 3 maths books and 2 physics books. Okay, now to work these out, you have to do each of them individually. So for them 5 maths books and not physics books, so out of the 8 maths books, you choose 5 of them, and out of the 6 physics books, you're choosing 0. So you're getting 56 for that one. Or, so you can see I do these on separate lines. This book is doing them all together, whichever you want. 4 maths books, 1 physics book. Okay, that's what you're getting here. So you're getting 420 options there. Or 3 maths books and 2 physics books, 840 there. and then because it's an OR, you add them all together. Okay, so in this one, let's try questions 6, 7 and 8. Okay, and I'm going to leave it at that for this lecture. Let me know how you get on WhatsApp, and then in the next one I'm going to go on to probability. Thank you.